talk of today will be quantum machine learning with subspace states. And Anupam from QC-Ware will be giving the talk.
Thank you. So I'll be telling you about some recent results on quantum machine learning for subspaces rather than vectors. And this is based on joint work with Ioannis Kerenidis and is available on the archive. So although this has been discussed in detail in the morning, I'll start by a quick overview of the desired quantum speedups as particularly applicable to quantum machine learning, and then tell you about the new results and the techniques that we use to obtain them. So in the context of quantum machine learning, I would like to formulate again 3 desired criteria, and the intersection of all 3 has been very hard to meet. So the first of these criteria is the quantum algorithm should be directly comparable to the classical algorithm and should be performing the same task. For example, it's not enough to sample from the solutions to a linear system and claim that it's same as solving a classical linear system. Second, the quantum algorithm should achieve a genuine exponential speedup over the best known classical algorithm. Like a high degree polynomial speedup doesn't suffice. The algorithm should be resistant to so-called dequantizations. And further, the problem should be useful in practice and widely applicable. For example, it's not enough to take Shor's algorithm for factoring and reduce it to some kind of machine learning problem, for example, SVM. So we would like to have a quantum machine learning learning algorithm that satisfies all these 3 criteria for speedups. And again, one may find that you can meet 2 of the criteria, but meeting all 3 has proven to be very hard to meet, and there are no known examples so far. So let's recall again the promising aspects of quantum machine learning. Like, why do we expect that or hope that these criteria should be met? So the first thing is about the exponential compression of representations. So for example, if you're thinking of the problem of representing a classical vector, so in a classical computer, you would store it as an array, and you would need space to be order n if you wanted to store an n-dimensional vector. So for example, if n was 16, then you would have an array with 16 cells, and each element of the array would represent some coordinate of the vector. Now, if one uses qubit encodings, it gives you access to the amplitude encodings of these vectors. And clearly one can see that an amplitude encoding, as on the second line, is an exponential compression compared to the classical encoding. So such an exponential compression raises the possibility of an exponential speedup for QML. But it should be very clear, even looking at this representation, that there are obvious bottlenecks to realizing this program, right? So state preparation in the generic case would might require circuits of depth n. There are certainly free parameters, order n free parameters in this quantum state. So you would need a circuit with at least n gates to prepare a generic such state. And secondly, when you measure the state, all this information is not accessible. You can only perform L2 sampling from the output. And with respect to this, like over the last 10 years, a number of QML algorithms have been developed. And if I were to classify them into families, I would name, for the near term, the inner product estimations and kernel methods, and then the more computationally involved algorithms of Hamiltonian simulation and quantum singular value transformation, which can solve linear systems and do more expensive computations using amplitude encodings. So again, it's quite easy to claim exponential speedups for QML, but one has to read the fine print. In particular, all these issues need to be addressed. First, the input issue of how do you prepare the initial state for the linear algebra procedure, for example. The output issue of the fact that the quantum algorithm is sampling from the output, while the classical algorithm is reconstructing the entire vector. The third issue is about the running time parameters, which should be interpretable and comparable to classical running point time parameters. For example, condition number may be rather difficult to bound, and this makes it hard to compare the classical and the quantum algorithms, and thus to establish speedups. And fourthly, particularly in machine learning, the matrices that arise are often dense, and they might have good low rank approximations or some other structure, but there's no reason to assume that they would be sparse. So all these caveats were known and were pointed out by Scott in 2014, and these caveats make it difficult to establish end-to-end speedups for QML algorithms. So on the next slide, I'm going to summarize in the intervening years what has been the progress towards addressing these caveats and what do we know at the present time. So for the input issues, like in quantum machine learning, we would like to work with generic data sets. So some solutions were proposed based on the quantum random access memory and data structures based on them. But as the QRAM remains an unrealized proposal, so these can be replaced with parameterized circuits in the near term. And in this direction, one can have logarithmic depth circuits, but for the unary and amplitude encodings of the vectors. For the output issues, in machine learning, there might be sampling tasks which are quite useful. For example, we had previously this work on recommendation systems, which worked purely by sampling. And today, I'll be speaking about the problem of determinant sampling, which is widely applicable in machine learning, and for which we'll see a polynomial speedup with quantum algorithms. And there's also the related literature about boson sampling and fermion sampling from the quantum physics side. So as for running time parameters, one may argue that if we are looking at low rank quantum linear algebra, then these running time parameters are the numerical rank and therefore a bit more interpretable. And in any case, over the years, our understanding for the parameters that enter into quantum linear algebra procedures has improved a lot, and we know exactly what these parameters are. As for dealing with dense matrices, so according to the state-of-the-art current results, we can operate with dense matrices as long as we can embed them into unitaries that are efficiently embeddable. So so if you have an efficient implementation of a unitary, so we can operate on submatrices of this unitary using the block encoding framework. So for today, I'll be speaking about a new approach to quantum machine learning with that works on subspaces rather than vectors, and will propose some candidate exponential speedups. So we'll come to that in a bit. So let me quickly recall the previous candidates for the exponential speedups and why they did not work out well and why we really do need new methods. So one of the better candidates for the exponential speedups, which addressed many of these caveats, was our previous work on recommendation systems, which tried to construct a quantum algorithm that works with sampling. So the quantum algorithm was designed to sample from the high value entries of a preference matrix without explicitly reconstructing the matrix. So thereby, this algorithm was avoiding the dependence on the dimension and had the dependence on the rank, and was considered to be an exponential speedup. Of course, under the assumption that there is good low rank approximation for the completed matrix, which is also made for all classical algorithms of this type. So the quantum algorithm had running time order k times polylog mn. So it avoided a dependence on the dimension and had a dependence on the rank instead. And this was dequantized by Tang in 2019, who showed that there's a classical algorithm with running time poly k and polylog mn. And since Tang's work, there has also been dequantization of many other QML algorithms, including the principal components analysis, the support vector machines, k-means, semi-definite programming, and so on. So a nice review paper by Tang and co-authors can be found if you look for it. So post-dequantization, what's the status of QML? So if we, so there are three things that one needs to compare. So the first is the quantum algorithm itself. The second is the best known classical algorithm for these tasks, and the best known quantum inspired algorithm for these tasks. So these are on the very left column of the table. The running time for the quantum algorithm scales as k. For the best known classical algorithms, it scales as a dimension and the rank squared. And the quantum inspired algorithm, the state-of-the-art ones, have something like a k to the 8 dependence on the rank. So one could argue that a speedup, a significant speedup with quantum algorithms with low rank linear algebra could be possible in some parameter regimes. For example, if you had a matrix with about 10 to the 8 users and products, then you can see the numbers on the right, which show that the quantum algorithm indeed seems to be doing much better in the numbers. But such parameters are certainly very far away from practice. Like in the current regime, we do not hope to achieve them anytime soon. So this makes it necessary to develop new techniques, since both the sparse HTL kind of approach and the low rank approach to quantum machine learning have serious limitations. It is a consensus that new techniques are needed to work further with QML.
But I'm Anupam, knowing that, this K to the 8 is certainly not a lower bound, right? Like, wouldn't we expect that it could be improved?
So maybe, but I would say that for now, let's say.
Yeah, sure, for now. Okay, but the other question was, so Tang's dequantization, does not seem to have been, adopted by anyone in practice, right? It's and I thought it was because maybe you were touching on this, but like it sounded like because the recommendation systems community kind of already moved on to other approaches, right? But does that suggest that even if we had a quantum speed up here, that like it wouldn't really be that useful in practice? Because if it was, then why aren't they using Tang's thing now?
What really has the order K dependence somehow, right? So if you believe in the K versus the dimension thing, so anyway, it's a question for when the quantum computers are able to get to that region, right? It's certainly not a question for now, right?
Yeah, but I'm trying to think ahead to that time, yes. And so, like what, even if we had the polynomial speed up for this recommendation system, would that even be useful?
So I would say that it's not just for recommendation systems. There's a spectrum of problems on the
sure, all sorts of,
some of them. So if not one, it might be useful for something.
Yeah. Okay. All right. Great.
It's the whole, at least.
Okay. Thanks.
So, so now for the new results and a new approach towards dealing with these things. So I'm first going to state the new results. So there'll be one polynomial speedup and two candidate exponential speedups. So I have to introduce each of these problems to you. So the first problem is that of determinant sampling. So this problem arises in machine learning whenever there's a trade-off between relevance and diversity. So for example, consider a setting where you're searching for images and your query is Jaguar, for instance. So if one queries only by relevance, then one is likely to get the most frequent items, which might refer to the car. But if one is in a setting where you want to find all the possible things associated with this query, where you want relevant as well as diverse queries, then you cannot do IID sampling. And in this setting, instead, the volume sampling is quite helpful. So for example, the feature vectors for very similar things like cars in the feature space would have very low. So when in feature space, they would be spanning a very small volume, while those for the diverse and representative elements would be spanning a large volume. So if there was a way to sample from the squared volume, one would be able to summarize the data set and obtain diverse features from it. So mathematically, the problem can be formulated as sampling a set of rows from a matrix with n rows and d columns, and the probability should be proportional to the squared volume. And this problem has found applications at many places in QML. So it's, for example, applicable to low rank approximation, to least squares, to finding representative summaries of data set, and even to some, and it even has some non-obvious applications to, for example, to finding the sparse, to find if your subspace contains a sparse vector and so on. So let's formulate this problem mathematically. So the input to the problem is a full rank matrix with n rows and d columns. And one needs to sample a subset of the rows. And these subsets need to have size d, which is the same as the number of columns. And the probability distribution for sampling a subset S is proportional to the squared determinant of A restricted to the rows in S. So the probability distribution that I'm writing here is correctly normalized. So this follows from the Cauchy-Binet identity, which shows that if I sum over all the sets S, then det A squared indeed sums up to det A transpose A. And this sampling from this distribution is an interesting problem because it depends only on the underlying subspace. It depends on the column space of A and not on the matrix A itself. So one can, so algorithmically, this means that one can pre-process the matrix to have orthonormal columns. And this is a strategy that's used for all the classical algorithms for this task. And this problem has been studied a lot in the classical literature over the last 20 years. And the best algorithm was, in fact, found in 2019 by Dzerzhinsky, Clarkson, Mahoney, and Warmuth. And And the guarantees for this algorithm are that it uses order d cubed arithmetic operations to find subsequent samples from this determinantal distribution. So the first result that I want to state.
Are big D and little d the same thing?
Yes.
Okay.
Sorry, that's a typo.
Sorry. So I mean, I know an algorithm to do this in time like n times d squared. So is that like the easy thing that they were improved?
So indeed, so first it was n d squared, that was 2006, then it was improved to d4 and d cubed.
Okay, fine. Yeah.
So the result here is that there's a quantum determinant sampling algorithm with ND gates and with circuit depth d log n. So for example, if we look in the regime where d is order n, then one would see the gate complexity of the quantum algorithm would be n squared, while that of the classical would be n cubed. So it's a polynomial speedup in this regime. And further, we'll see that there are some the matrices with low complexity somehow. So I'll define the complexity measure. So there's a possibility for a cubic speedup for certain kinds of matrices. But in any case, so this is at most a polynomial speedup, and it's for the determinant sampling problem. So that's the first problem we'll be talking about. So the second problem it comes about is regarding compound matrices. So for any n times n matrix, I can define a kth order compound matrix, and let's look at this definition a bit. So it's so this matrix will be indexed by the size k subsets of the rows and columns of A, and the corresponding entry will be the determinant of the corresponding minor. So think of this as a huge matrix with dimension n choose k by n choose k. So there are n choose k rows and n choose k columns. The rows and columns are indexed by the subsets of the rows and columns of A, and the entries are given by the minors. So here the theorem is that there's a quantum algorithm which can perform singular value estimation or transformation for the compound matrices of all possible order k's, so for all possible sizes of the subsets k, and it has complexity poly n. So the compound matrices are rather interesting because they have this kernel property. So every spectral property, for example, of the matrix A often generalizes to the compound matrix. If A is unitary, then its compounds will all be unitary, and if it's A's PST, all its compounds will be PST, and so on. And these compound matrices have in fact been found to be quite useful in machine learning. So Vishwanathan and Smola found that many of the kernel methods, like the Cauchy-Binet kernels, which are based on the compound matrices, generalize many of the kernel methods that were commonly used in ML, and especially to data that varies with time. So let's speak about the nature of the speedup a bit. So the classical algorithms would have naively complexity n to the k for dealing with the compound matrix SVD, and better algorithms have not been found so far. So this is a potentially exponential speedup. If we look at the quantum-inspired algorithms literature, so all these algorithms have running time polynomial in the matrix rank. But one can in fact show that if A has rank R approximation, then the rank of the compound matrices R to the k. So this will be exponential in for large enough k, and so one would need new techniques to dequantize the compound matrices. So of course, the open question is to find end-to-end QML application using these compound matrix SVDs as a primitive.
And what about the SVD? Do we want like just to calculate a given singular value or to sample from the singular values? Because there will be exponentially many of them, right? It's an n to the k by n choose k by n choose k matrix.
So you can do exactly the same thing, create a superposition of things, and then estimate these eigenvalues like in phase estimation, or put them in amplitudes. Like the entire toolbox generalizes this.
Oh, all right. Fine.
So the third result is about topological data analysis. So it's n choose k by n choose k, so certainly it's square. And yeah, it seems to be symmetric by the definition because H is ij or ji. Okay, let's take this offline if you think that there's a problem with generalizing this toolbox.
No. I just think that it's probably because it's schematic, it's essentially just data.
So we'll see how this arises naturally out of the Hamiltonians. So maybe we can take this question after we go through this. So the third application is to this problem called topological data analysis. So as this is not a very common problem, I'll say something about it. So in the perspective of ML, it is useful because it captures the topological, the global features of the data set, and it's somehow complementary to the other machine learning methods that are commonly used. I'll try to do a very quick formulation of this and show you that it does arise naturally from your data sets. So topological data analysis is formulated on simplicial complexes. So these one can think of as a generalization of graphs. Besides vertices and edges, they have faces, high order faces. So they have faces of order 3, 4, and so on. So given your data embedded in a metric space, one can there's a natural simplicial complex associated with it. So it's called the Vitoris-Rips complex. So X is the point set, which is in the matrix space. It has n points. And the simplicial complex will include all the point sets which have diameter at most t. So there's a scale parameter in the Vitoris-Rips complex. And this is a natural simplicial complex that you can associate with your given data set. So now TDA is about the spectral properties of the Vitoris-Rips complex. So one can define canonically a Dirac operator on this simplicial complex and a Laplacian, which is the square of the Dirac operator. And then the dimensions of this graded Laplacian operator, graded because it's defined on the order 2, order 3, and so on faces. The dimensions of the kernels of this graded Laplacian are the Betti numbers. And the claim for topological data analysis is essentially that the persistent meaning those which survive over a large number of distance scales, Betti numbers for these Rips complexes, capture shape features of the data and are somehow useful and complement the other classical ML methods. So TDA was introduced to quantum algorithms by this seminal work of Lloyd, Garneron, and Zanardi in 2016. So they observed that the Dirac operator is exponentially large and sparse, and so one could use Hamiltonian simulation and use it for quantum TDA. But so this approach was using phase estimation and had large polynomial overheads for the reasons. The Dirac operator simulation was not efficient, and Hamiltonian simulation has its overheads as well. And this has actually been quite an active topic of research over the last few years. And people have come up with constructions which reduce the depth to order n. So the new result here is that there's in fact a log n depth embedding for the Dirac operator. So that gives you a quantum TD algorithm with polylog overheads. So yeah, so I think that's a discussion of the results. I'm now going to move into the techniques.
So this last result that you are is something upcoming work, or we have a citation for this?
So it's the same work I'm talking about. So this work has 3 main results, we think.
Wait, the Dirac operator is a 2 to the n by 2 to the n matrix, and you can do it with only log of n depth.
That's the main thing.
Okay. Wow. Okay. Oh, well, I guess analogous to the QFT.
And obviously the QFT indeed. So that's one of the efficient operators that could be useful. And we'll see shortly how this efficiency is coming up.
Why is this operator called Dirac? The way that you're using it, it looks more like the differential of a chain complex.
So indeed, it's also the boundary operator for the chain complex. So it was introduced to quantum mechanics by Dirac. So it also goes by the name of the boundary operator.
Okay. Well, this is just semantics, but I thought the Dirac operator was something else. Well, Dirac did many things. Yes, the boundary operator, its adjoint is what's in your formula, really.
Yeah, so B is the boundary operator plus its adjoint, and it squares to the Laplacian.
Sure.
I think it's called a Dirac operator in the sense that it squares to a Hamiltonian in that sense.
That's all it takes. Well, that's a separate. Okay. Anyway, the question was answered.
So the central idea which ties together all these results is this notion of subspace states. So which eventually, which ultimately derives from the fact that the orthogonal of the unitary group acts not only on vectors but also on the higher dimensional subspaces sitting in R, for example. So I'm going to give you a definition of the subspace state. So it's highlighted on this equation. So to represent the subspace, one can represent it using a matrix X with n rows and d columns. So this is a d-dimensional subspace, and the matrix X is supposed to have orthonormal columns, and the column space of X is the subspace under consideration. So the quantum representation for this subspace, this quantum subspace state, is exponentially large superposition. So it's a superposition of bit strings over bit strings with Hamming weight d. So that you can think of as subsets of the rows of the matrix X. And the corresponding amplitudes are the determinants of the X restricted to the rows in S. So in fact, this is a one-to-one encoding for subspaces. It depends only on the column space of X and not the representing matrix X. And this is because the determinant remains invariant if you apply column operations to it. So in particular, if you apply a unitary V on the right to X, then you do get the same state. So as we see, like all these subspace states are a part of the Hilbert space of Hamming weight D, but they are actually a very small part of it. So a subspace has only ND parameters. The Hilbert space has n choose D parameters. So the subspace states form a very special family of the level D Hamming weight states. And one particular thing to note is that all the standard basis states are the subspace states because they correspond to the matrix which has some ones in each column, and there's exactly one determinant, that's one, and that corresponds to this. So this notion of subspace states will be sort of integral to all the things I'll be describing here. So if we look just to what's the motivation of subspace states on the QML, of what implications it might have for the near-term QML, right? So the near-term QML is basically based on using unity encodings of vectors and trying to do different kinds of inner product estimations. So one can ask the question of what the inner product between the subspace states is and how does it generalize the inner product between vectors. So the inner product between the subspace states is determinant of X transpose Y if you are calling the representing matrices X transpose Y, and it's the product of the principal angles between the subspaces. So the inner product between a pair of vectors is just the cos of the angle. The inner product between subspaces is the product of the cosines of the principal angles. And indeed, this kind of thing has also appeared in classical machine learning. So the work of René Vidal has been on trying to classify and cluster using subspace representations. And it may be relevant to settings where the data has a natural representation in terms of subspaces, for example, images or video where you're compressing things and representing your subspaces. So that's just a slide on why this might be relevant to QML in the near term. So all the interesting algorithmic aspects of this work are so one can ask what are the possible quantum operations that one can do on these subspace states and how do you prepare them after all. So, and how this relates to the results that I was describing earlier. So on this slide, I'm going to list all the operations you can do, and then we'll look into the algorithms that we have for doing them. So the first operation is measurement. So if you measure the subspace state in the standard basis, this is equivalent to solving the determinant sampling problem. So this follows right from the definition. So if I can give you an efficient procedure for producing these subspace states, then I also have a solution to the determinant sampling problem. So the next operation is addition or deletion of vectors to your subspace. So I'll present some efficient quantum circuits which add or delete vector y from to a subspace column X. And the third operation that we can perform is to rotate the subspace. So for example, given the subspace column X, how do I create the subspace called UX, where the unitary U is being applied from the left? So we saw that when we apply it from the right, the state does not change. And one notion that will emerge for these algorithms is the Gibbons complexity of the unitary, which is the number of elementary Gibbons rotations that appears in a decomposition of the unitary. So let's relate it to the three main results that we said. So measuring the subspace state solves the determinant sampling problem. And the compound matrices and the TDA algorithms will follow from the unitaries that we construct for addition and deletions of vectors and rotations. So we'll be constructing certain unitary operations that act on subspace states, and these will be embedded as block encodings in these bigger unitaries. So that's somehow the framework of how this all fits together. So I'm now going to describe to you this method for addition and deletion of vectors and how it relates to mathematical technique that is interesting here is our operator systems, which are generated by mutually anti-commuting operators. So these form the classical Clifford algebras. So interestingly, while you can have any number of commuting operators on a Hilbert space, even of a small dimension, the dimension of a Hilbert space, which has 2n plus 1 mutually anti-commuting operators, must be exponential. So this is a classical result of Herman-Weyl, that if you have 2n plus 1 mutually anti-commuting operators acting on Hilbert space H, then H must have exponential dimension. And there's a nice quantum proof of this, where a pair of anti-commuting operators induces a tensor product factorization of H as H1 times H prime, where H1 is a 1-qubit space with 2 of these anti-commuting operators acting as X and Z. And it's implicit in the quantum verification paper of Reichert and Bazurani. So the importance of this is that there's a one-to-one mapping between the space of n qubits and a system of 2n mutually anti-commuting operators. And in fact, there's a canonical set of mutually anti-commuting operators, which can be defined as z I minus 1, x I n minus I. So z on the first I minus 1 coordinates, x on the ith coordinate, and identity on the rest. So one can check that these form a system of mutually anti-commuting operators. And a uniqueness result tells you that up to unitary conjugations, this is the only kind of system you can have. So I'm going to relate this to the subspaces shortly. So the relation between the two was is the gamma map, which was introduced by Dirac for his equation in 4 dimensions, for example. And this can be used to lift your vectors, matrices, and even higher order tensors to operators and to operators in the Clifford algebra. So the gamma map for a vector is defined as follows. So it is so just as the amplitude encoding of the vector was xi and coupled with a state. So now we are writing a sum over these mutually anti-commuting operators, which are canonical in some sense. So gamma x is xi times one of these mutually anti-commuting operators. And the mutual anti-commuting nature of these operators gives you a very interesting property of the gamma map. So if you're talking about a unit vector which has norm 1, and you square this gamma map, then it squares to the identity, and therefore it's a unitary operator. So this raises the natural question of what's the complexity of implementing these unitary operators. And we'll see that all the power, like the new efficient operators in this context are these implementations of these gamma maps. So the gamma map, again, you can think of it as embedding a vector as a sum of mutually anti-commuting operators, and the anti-commutativity ensures that it's a reflection. And so a Clifford loaded circuit, we define it to be an implementation of this gamma map unitary. And one of the main results about the Clifford loaded circuit is that it performs this addition deletion operations on subspace states. So when you apply the Clifford loader to column y, and if x is orthogonal to the subspace y, then you get the subspace state represented by appending x to y. And similarly, if x already belongs to column y, then you get the state which you obtain by deleting y from this subspace. And the general case, of course, will be a superposition of these cases. So one can completely analyze the action of the gamma map on these subspace states. So that immediately gives you a procedure for preparing the subspace states as well. So if you want to, if you have an orthonormal basis for your subspace, then you just need to apply the Clifford loaders corresponding to these orthonormal vectors. So you apply CA1, CA2, and CAD to 0n, and by this theorem you would be getting the subspace state A because you've added to 8 orthonormal vectors in each step. So of course the question is, how do you construct the implementations of these unitary maps? And this is closely related to the unary encoding problem in quantum machine learning. So to prepare unary encodings of vectors, one uses logarithmic. So we have these unary data loader circuits, so which can be thought of as logarithmic depth state preparation circuits. So these are structured like binary trees and have gates which are the beam splitter gates. So I'll be defining these gates shortly, and these have n qubits and depth log n. So for example, the figure on the left shows you the data loader or the state preparation circuit for a vector of dimension 8, and it has depth 4, which is so the 2-qubit gates used in this context are the RBS gates, which act as identity on 0, 0, and 1, 1, and rotation on the rest. And one can define not only these RBS gates, but fermionic analogs of these RBS gates. So the FBS gate acts as either RBS theta or RBS minus theta, and and this depends on the parity of the intervening qubits. So if the parity of the qubits between I and j is even, then it acts as RBS theta. Otherwise, it acts as RBS minus theta. So this is the fermionic analog of the RBS gates, which we call the FBS gates. So I'm going to describe to you now the Clifford loader construction. So the Clifford loader circuit, or the implementation of the gamma map, is obtained by first replacing all the RBS gates in your data loader by the corresponding FBS gates. So make all the gates fermionic, and then conjugate. So sandwiched between an X on the first qubit and I on the rest, between 2 fermionic loaders, gives you the gamma map. So this is again one of the main results on the Clifford loaders. So here is a picture of it. So you can see that there's an X in the middle, and the circuits on the left and the right are obtained from the unary data loader by making all the all the RBS gates into FBS gates, which entails certain extra control X and control Z gates. So this is the construction, and essentially it's log depth, and all the results derive their power from this implementation of the gamma map. So if you want to look into the proof of this construction, then one has to look on the action of these gates on subspace states and relation with Gibbons rotation. So as I'm coming to the end of the time, I'll skip the proof details and just give you a quick overview. So again, the main result, that the one worth remembering, is this lemma that the action of these FBS gates on the subspace states implements a quantum Gibbons rotation. So a classical Gibbons rotation takes 2 rows of your matrix and takes a linear combination of them. It adds cosine of the first row plus sine of the X in the second row, and so on. So classically, such a Gibbons operation would cost k arithmetic operations if you had k rows in your matrix. But quantumly, you can implement it with a single gate on the subspace state. So the FBS gate acting on the subspace state implements a Gibbons rotation. So this fact was already known for the RBS gate and used quite frequently in the chemistry literature. But these longer range FBS gates certainly seem to be new. And then let's look briefly with the compound matrix SVD. So if one, so there are 2 ways for subspace state preparation. So the first is to decompose your subspace into a sequence of Gibbons rotations and then replace each one by the corresponding RBS or FBS gate. So this gives you what's called a Gibbons circuit. And if one looks carefully at the Gibbons circuit, one finds that it has the compound matrices embedded in it. And not only that, So the given circuit is unitary, so it has the compound matrices of unitary matrices embedded in that. So not only that, if you use a block encoding for A, then the compound matrix UK is a block encoding for AK, and all the quantum linear algebra techniques carry over to the setting. So that's at the high level how you get the compound matrix SPD. And the Dirac operator embedding is similar. So if we look at the unitary implementing the gamma map, so one finds that the Dirac operator for the complete simplicial complex is the gamma map for the uniform vector, which has all the coordinates equal to 1 by square root n. And the Dirac operator for an arbitrary simplicial complex embeds as a submatrix of this. So that also gives you a block encoding for the Dirac operator for an arbitrary simplicial complex. So by looking at the matrices which are embedded into these unitaries that we use for constructing the subspace states, one gets these two new kinds of algorithms. So to summarize, we saw three problems: determinant sampling, compound matrix SPD, and TDA. And we introduced some new quantum tools to deal with them. So the first were Clifford loaded circuits, the second was given circuits, and the third was this efficient embedding for the Dirac operator. So for determinant sampling, the best classical technique is importance sampling, and the quantum speedup is polynomial, n squared versus n cubed in general case, potentially cubic if your matrix has low Gibbons complexity. For the compound matrix SVD, the best known classical algorithm would be some kind of SVD, and this speedup so far seems to be a high degree polynomial or an exponential speedup. And for the Dirac operator embedding, the speedup is in the depth, like the previous depths were order n, and this is now a log n depth. So if one looks for the research questions that arise out of this, so the first two are obviously to find end-to-end QML applications using either the compound matrix SVD or the topological data analysis, which take into account all the factors and have a potentially exponential speedup. And another research direction is to look for bosonic compound matrices. So these would be indexed by multi-sets with scaled permanence instead of the determinants as entries. And develop NIST methods for quantum SVD with these bosonic matrices. And perhaps they have applications to ML. So let's conclude with some high-level takeaways. So from this work, it seems that one of the promising avenues, if you want to obtain exponential quantum linear algebra or ML speedups, is to find matrices that embed in unitaries which are associated with non-interacting fermions in this case, but other quantum systems as well could be candidates for such kinds of speedups. The second message is that QML can be formulated to work not just with vectors, which are one-dimensional subspaces, but for subspaces of arbitrary dimension. And the third being that if one needs to obtain a quantum speedup in an applied domain, you don't necessarily have to fit your applied problem to the quantum technique, but looking at problems which are closely related to quantum mechanics may be another way to do this. Let me stop there. Thank you.
Thanks a lot, Anupam. Questions?
Yeah, quick question. So you were talking about the depth for the case of TDA. I wonder, can you remind me if the depth is proportional to the size in this case, or is it exponentially small? So,
sorry, could you repeat it? The depth versus what?
The circuit depth versus the circuit size. I was wondering, if it's how those compare for those numbers you gave.
Depth is log n, size uses n gates.
So then the final result is for the scaling, will it be still O tilde n if you're interested in size? Because you go back to the slide that has the scaling on it. Go forward a bit. Like it's near the end. Right here. So my question is, if I replace circuit depth with circuit size, would it be something like order n log n, or?
So the previous circuit probably had depth n and.
Well, I'm not interested in depth at all.
Sure, you're talking about the size. Right?
Circuit size is the only thing I care about. Okay. So what's the circuit size?
So it's log n in depth and n in size.
Oh, okay, great, thank you.
The new construction. The old one is some polynomial.
Yes. Thanks.
Any other questions? Yeah.
there any challenge that is associated with the rescaling factor for the block encodings for those Dirac operators?
So indeed, there will be a rescaling factor, and this is so at least for the this is optimal for the complete simulation complex. So it's indeed a unitary and it's embedding. The scaling factor essentially arises because so the best you can hope for is the spectral norm of your operator that you're embedding, and then you have some additional scaling factors. So it's optimal for the complete simulation complex. And then, of course, to do TDA, you also need efficient implementation of the memory overlapping for the simulation complex.
So this polynomial speed up or potential polynomial speed up for determinantal sampling, it seems like it's analogous to like a potential polynomial speed up that you could get for like just sampling the outputs of Clifford circuits.
So that's how it's coming out, right? The Clifford circuits naturally encode the determinant because there's a lot of cancellation going on there. So
right. Yeah, but which like again, it's like an n cubed versus n squared type of thing, right? With
n cubed versus n squared.
Yeah.
But so, for example, if your unitary had, if your subspace could be written as a product of n log n given rotations,
right,
then it would be a cubic speedup.
A cubic speedup.
If
Okay.
Or potentially cubic, like the classical people need to look at what happens when your matrix has low given complexity.
I see. It would be nice to like understand this analogy in more detail. Like, can you view the fermionic beam splitters as just some kind of analog of the Clifford group, or are they just two subclasses of quantum circuits that are just both efficiently classically simulable for reasons of linear algebra, but for different reasons?
So you want to see an analogy with the Clifford group?
Yes. And they both seem to admit, some potential polynomial quantum speed up for a sampling test. Anyway, although maybe the determinant one is of more practical interest. Anyway, just a thought. So, all right, so it's the end of the time. So let's thank Anupam again. Back on, yes.